So we calculated the fermion determinant. We expanded it in power series of the background gauge field. There was the sum of infinite number of terms, which can be organized as sum of one loop graphs. All of them produce one loop graph. And today we are going to look at the leading term in that expansion. The leading term will have two external A lines. So this is called vacuum polarization. In QED. And let me just remind you the formula that we obtained. I introduced a function of WA, which started with a classical term, classical Maxwell-Lagrangian, plus the sum of infinite number of terms which came from the expansion of the fermion of the Dirac operator in the background of the A field. And the first leading term in that expansion, if you go back to your notes and look at them, will be written, it will have 2 powers of A X space. Then there is a trace for fermion labels, spinor indices y1 minus y2, gamma mu s y2 minus y1 times gamma nu. And we saw that this minus comes because of the fermion loop. So if you want to represent this as a graph, as a Feynman graph, it will be a one loop graph with 2 external A lines, and the usual. So this is a propagator. This is one vertex. That's another vertex. This is the A mu line. This is minus I comma mu. This is the A nu line, and this is minus I comma nu. And recall that we put the coupling constant in front of this term, so it is absent from here. Otherwise, the vertex would be minus I times E times gamma mu and gamma nu. Okay? As is more common. So the E is missing from here because it's standing here. You can redefine A. Obviously, if you send A to E times A, it will disappear from there, it will reappear here, and therefore the vertices will be minus IE times gamma. Okay? This is a convenient way of writing it so that it simplifies the writability. Our aim is to calculate this term. Today we would like to calculate this term. It's a one loop graph. And so you expect it to be divergent, and you would like to understand the nature of this divergence. It's an important calculation both for physical reason and for technical reasons. The physical reason is that, as we shall see, you can use it, for example, to find correction to the Coulomb law, the correction which comes from quantum effects of fermions. And technically it's important because it has, we will understand a little bit about the gauge invariance, the effect of the quantum loops on the gauge invariance. So far we have been dealing with the scalar fields, and there was no issue of gauge invariance for the scalar fields. Right? But here now we have a vector field, so the gauge invariance is a non-trivial problem, especially because the expression that we are handling, as you will see, is singular, it is divergent. It is divergence and the gauge invariance we have to understand the interplay between the two. And this is a non-trivial problem. It's a technical problem, but it's a non-trivial technical problem that you have to understand well. Okay? So, let's proceed then. To proceed, I am going to introduce a label, a notation. There are plenty of factors of i's floating around. They will disappear in a minute. So let me introduce the tensor, which I'm using essentially the same notation. I'm using the same notation which I use for the scalar field. Which I use for the scalar field. Then in the pi, in x space, it's basically all the expression which is standing from here to here, in which you have thrown away the integral of the a's. That means the integrand here, essentially. So it's equal to this trace of the loop part. The essential part of this calculation is the loop part. This is really the part of the calculation we need to understand. I mean, after we go to the Fourier space, it will be a loop integral, as you will see.
There will be a mu index on the tensor, on the left-hand side.
Yes, our pi mu. Yeah, thank you. And to proceed, we are going to substitute everything in terms of the Fourier expansions. So S, we know what it is the fermion propagator. We worked it out last time, and we saw that its Fourier expansion is given by I over P slash minus M plus I epsilon exponential of minus I P dot Y1 minus Y2. Likewise, we will substitute for A in terms of its Fourier expansion and simplify the whole thing. And the bottom line will be, I think you can all do this Fourier expansion, no? Yeah. You can do, also you should expand that term in order to write W in a compact form. With W becomes E for K or 2 pi to the power 4 times. There are two contributions. One is coming from the classical piece, which has 1 over E0 squared in front of it. And you know that F mu has d mu a nu minus d mu a mu. When you go to Fourier space, it becomes k mu times a. So that term contributes, after you simplify it a little bit. Let me put the factors of a outside the bracket, because it's common to everything. There is 1 over E0 to the power 2, which indicates that this term is coming from the classical part, minus k squared a mu nu plus k mu k nu, and then the Fourier transform of this object, minus pi mu nu k close the bracket a mu to the k. Okay? So what I've written there is this expression, after simplifying the i's, etc. This expression written in Fourier space. Remember that in Fourier space, this will become, it's d mu a. E mu in Fourier space becomes
K.
I times k. I k mu a tilde nu k minus I times k nu a tilde k. And when you square this, there will be k square terms coming from that. These are, they combine to this part. And then this term is, we are going to work it out. I've just plugged in, for the trace here, I plugged in pi mu nu y1 minus y2 and to Fourier transform and call it Fourier transform pi mu nu k. Maybe I should do a tilde on top of it. Okay? Is clear, the notation? Yeah. And from the definition, you see that what pi should be. So I'm dropping the tilde from pi because this is the only pi we are going to use. We are not going to use the x space pi. So if you simplify that relation, you will find out that it's given by d4p 2 pi to the power 4 trace of, and the rest is clear. You can use also the cyclic properties of the trace, etc. to write them in a little bit organized form, multiply with the inverse of the term, and or conjugate of the term, write as p slash I p slash plus m divided by. Are you familiar with what I'm doing? You must have seen this before, no?
Yeah.
In the course of Giovanni. Normally, when you have the fermion propagator, you multiply the numerator and denominator by the conjugate of this term to bring the denominator to the standard form times gamma nu. It's a one loop graph, so apart from the matrix index, it is very much like the one that we did for the real scalar field. From that point of view, it's not different. So that's the definition of pi. What I have done is just a Fourier transform this expression, and the substitute for S is Fourier transform, and the result becomes there, what you see. Okay? And this i's, of course, come from the numerator of the propagator. Any questions?
Actually, A nu k, is it similar to polarization of proton?
Sorry?
If you take Fourier transform of proton field, is it polarization?
Sorry, I couldn't hear what you said.
I mean, the expression, I mean, A nu k.
Yes? This one?
Yes.
Yes?
Is it same as polarization of proton?
Well, for what I'm doing, it's a background vector field. But when you go to the quantum theory and quantize this, yes, the polarization of the photon comes from this field. So when you quantize the free photon field, then the polarization of the photon is essentially the momentum space wave function of the photon. It's like the UP for the electron. But for now, it's just a background electromagnetic field. Okay? So essentially what we are calculating, that phi is this graph with P here and P minus K here. It is just this graph without the external lines. That's pi. So if we want to write it graphically, I mean pi is this. There is one vertex there, that's P minus K. And put the arrows like that. Thing like this. Okay? Good.
K slash.
K slash, yes. Another difficult thing to write in LaTeX. Okay, now from here it is the monotone of tracing and doing various things. The first thing you note is that the trace of an odd number, the product of odd number of common matrices vanish. So you see that here we have maximum the product of 4 matrices. 1, 2, 3, 4. Okay, each one of them has a common. The minimum is the n term here, gamma times m times gamma times m2. And there are terms with 3 gamma matrices in them. So use trace of gamma 1, gamma mu 1, gamma mu 2, gamma mu 3 equals to 0, and the only things which will remain will be the trace of the product of 4 gamma matrices or 2 gamma matrices. Okay? And that simplifies the expression a little bit. So this becomes, let me put the quality here, P4, P2 pi P4, trace of gamma mu P slash gamma nu P slash minus K slash plus m squared gamma mu gamma nu divided by P squared minus m squared plus I epsilon times P minus K squared minus m squared plus I epsilon. So the first term has the product of 4 gammas and the last term has the product of 2 gammas. That's the last term is obvious. Gamma times m times gamma times m. That gives rise to that. And then the rest is gamma times P slash times gamma nu P minus K. That's the term with 4 gamma matrices. The next step is to put the denominators together using the Feynman trick that we used, I think, once or twice before, and then shift the integration factor. Now, you can actually do the trace of the gamma matrices, and we are going to use dimension regularization. So let me first tell you what we are after. This calculation, apart from its usefulness for finding things like correction to the Coulomb law, should give us something which is good, in the sense that this term, you see from here that that term is given by this integral, and this integral is quadratically divergent. Okay? There are 5 powers of p in the numerator and 4 powers of p in the denominator. So this 4 plus 5 minus 4, it's divergent, it's linearly divergent. It's not linearly divergent. It should be, no, I'm wrong. I have 6 power of p numerator. So this 1 times 2, that's 2, with 4, that's 6, divided by p to 4, so it is quadratically divergent. So this is given by a divergent integral. We would like to show that dimension regularization will make this tensor proportional to this tensor times the scalar quantity. So our aim is, this is one of our aims, is to show that pi mu nu k equals to the same tensorial structure that you have in the free case times a Lorentz invariant function of a scalar function of, not Lorentz invariant, scalar function of k squared. Okay? So essentially our problem would be the calculation of this expression. If you use dimension regularization, you do not expect that for a model like QED, you do not expect that gauge invariance depends on the dimensions. Whether you are in n dimensions or in 4 dimensions, the gauge invariance should be the same. Therefore, on that ground, we expect to have something like this. But since we are dealing with singular integrals, we would like to check that. Okay? And a good exercise for you is that to evaluate the same thing using some other regularization. For example, just put a momentum space cutoff and see what you will get. And then you'll be able to compare the usefulness of dimension regularization with something like a momentum space cutoff. In fact, I've composed an exercise on that, but since I couldn't print it, I will send it to you later. So this is what we would like to do. This is one of the things that we would like to do. We would like to show that by evaluating these traces and regulating, etc., the result will have that form. And you will see that there are non-trivial cancellations in order for it to come out. And we are going to use dimension regularization, but we are going to use dimension regularization to regulate the integrals over P. Therefore, we are going to evaluate the traces in 4 dimensions. So we will evaluate the traces of the common matrices in 4 dimensions and then apply dimension regularization to regulate the integral over P. And in order to fit this whole calculation in 1 hour, I am going to sketch the steps and give some detail of the calculation. So the first thing that you can do, or you should do, if you want to follow this way of evaluating that integral, is to use always the Feynman trick to put the denominators together and write them as a single denominator with 1 higher power. So here you have the product of 2 factors. We are putting the 2 factors together and writing as a single expression power 2. And for it, take this to be A and take this to be B. And then in the resulting expression, if you remember from the way that we did for the scalar theory, we will shift the integration variable P from P plus something else. I think I'm going to skip these steps because they're exactly identical to what we did for the scalar theory, and just write the result. The difference, of course, is the amount of calculations. Since here you have a non-trivial numerator, when you shift the integration variable P from P to P plus x times 1 minus x times k, then there will be extra terms which will appear in the numerator. Do you remember what we did for the scalar field? We had a loop like this for the scalar field where we did precisely the same operations. If you don't, of course, you should go and look at your notes and repeat this calculation for yourself. After making that shift, the denominator will have a clean p squared times so the structure of these integrals, the one loop integrals, which have only two vertices, is always the same thing. The only thing which can change from one to the other, one theory like the scalar field theory, phi to 4 scalar field theory, or phi cubed even for the self-energy graph, and this one is just the expression in the numerator. The denominator always will come to the same point, to the same form. And this is plus here. Okay. Now, the trace of the gammas can be evaluated by the way, you can regulate this also using the so-called power in large regularization. It will also produce a structure like this. So the result of the tracing will give us, so do the trace over gamma matrices. And now that I have done the trace and all that, I'm going to write the integral in n dimensions for dimension regularization. The tracing produces a factor of 4 times 2 p mu p nu minus eta mu nu p squared plus x times x minus 1 times 2 k nu minus eta mu nu k squared plus m squared times eta mu nu divided same denominator. We have not done anything on the denominator. Okay? So, if the numerator was 1, this integral would be exactly what we calculated for the scalar loop. But in the numerator, you have terms which are dependent on p, and they are integrating over p, and then a number of terms independent of p. The part independent of p is just 1 divided by this denominator times these terms, which is the one for real scalar field. The ones dependent on p give you a different integral, the ones that you have not seen before. Because what you have seen before is just 1 divided by this expression. Now we have a quadratic function of p divided by that expression. But this is easy to bring it to the form that we had before. The way you do it is to note that in fact, it's easy to calculate. I will tell you in a minute, a more general integral from which you can obtain all these integrals. So a kind of generating function for these integrals. This integral by Lorentz invariance on the right hand side should give, by Lorentz invariance of dimensional arguments on the right hand side should give you a second rank symmetric tensor. No? And the only thing it can be is just eta. Right? So this integral will be, in fact, eta mu nu divided by n. It's the same integral as dnp divided by 2 pi to the power n times p squared divided by the same denominator. First of all, if you take the trace of both sides, this will be p squared, this will give you n times divided by n, it will be 1, it will be equal to this. Okay? But in order to get all these integrals, a good exercise is just calculate the following integral. You can calculate this integral with any power alpha here. Any integer power alpha like here. Here alpha is 2. So this will be obviously a function of k. After we have done that, by differentiating with respect to k, successively, you will bring powers of p mu on the numerator. So differentiate by respect to k mu1, k mu2, etc. It will bring p to the numerator. So it's just sufficient to calculate this integral. Then from this, you can obtain all the integrals like this with any power in the numerator and the n number of p's in the, with any power alpha in the denominator and any product of p's in the numerator. Okay? So, now putting this back here, then these two terms will be like each other, except that in front of this there will be a factor of 1 over n. Both of them are proportional to eta mu nu times p squared, and the denominator is the same for both of them. So therefore, the only integral we will need to evaluate will be p squared divided by this denominator. Okay? That's the only thing we need to evaluate. Apart from the 1 over 1 divided by this denominator, which we already have evaluated when we were studying the one loop correction to the scalar propagator. So therefore, we need only two formulas for the integrals, n-dimensional integrals, both of which you can obtain from this exercise, which I gave you. If you solve it, you can get the result for any integral of this kind, not only these two, but any other integral also. So let me just quote the formula for the integrals. So we need you have to do the usual Wick rotation, etc. This turns out to be minus I over 4 pi to the power n over 2. It's a very good exercise to reproduce these things so that you have some confidence about expressions that you encounter when you use dimensional regularization. This is the expression that we had called a squared in our previous calculations. Now the power here is 1 minus n over 2. And the other one is with 1 in the numerator, which we had before. let me just put it here. It is the same denominator to power 2. And here it is plus I over 4 pi n theta 2 gamma of 2 minus n divided by 2 divide the same denominator, but the power is 2 minus n over 2. Here is 1 minus n over 2, here is 2 minus n over 2. Now we have to, I'm just sketching the steps. We have to plug this in here. After we have done that, there will be a 2 over n times p squared times eta, and here is minus 1 p squared times eta. Obviously, both of them will lead to an integral of this form, times a number, times eta mu times 2 over n minus 1 will come from here. And from here, it will be this expression times this. Okay? So the coefficient which will come from here, obviously, is from here you will have a factor of 2 over n minus 1 times eta mu. Then there will be a p squared, which we have to integrate over. So put them together. Are you following me? I need, where should I write? Maybe I can erase this part, but we don't need it anymore. So remember that from here we will have that factor. Let me work out these factors, and then it will be this times eta mu. Just to remember that it's coming from the first term. Because this is effectively, this term is replaced by p squared over n times eta mu. And then it will multiply the n-dependent objects from here, which is n over 2 times gamma of 1 minus n over 2. Of course, the denominator will write through. I'm not writing denominator. I'm just writing the factors of n, or the factors which depend on n. That is n over 2 times gamma function times an n-dependent quantity coming from the numerator, which is that. Okay? But you see, if when you multiply this, n over 2 times 2 over n gives you 1 minus n over 2. So this part then becomes 1 minus n over 2 times gamma of 1 minus n over 2. And what's this? This is z times gamma z. Is gamma of z plus 1. So it becomes gamma of 2 minus n over 2. So it becomes the same gamma function which is on the numerator of the second term. But the denominators are different, because this has a power 1 minus n over 2, this has power 2 minus n over 2. Okay, so when we put them together, it's better to write the denominators also like each other, like a single denominator. So we should remember that from the first factor, we will get a clean gamma of 2 minus n over 2. When you take care of this n over 2 from here, gamma function from there, and 2 over n minus 1 from here. When you put all of them together, effectively this numerator will become, so effectively this will go to gamma of 2 minus n over 2. if you take this part into account. So if you multiply this by 1 minus n over 2, which will come from here, and then that will be the result. The reason I'm writing it in that scattered form is that I need a blackboard, so I have to clean this again in order to write the rest of the expressions that I want to do. Now, in the rest, as I said, the denominators are different. They have different powers, but we can multiply this by a factor of this expression here, and then write this as 2 minus n over 2. Means we can write 1 minus n over 2 equals to the same expression divided by 1 minus the same expression divided by the same to the power 2 n over 2. In this way, the denominators also will be like each other. So, in the numerator, both of them we have comma of 2 minus n over 2. In the denominator of both of them we have the same expression. We have to remember that this expression will be multiplied, we have to still multiply it by that. That one we have taken care of. By everything. But this one should be multiplied with this other expression. And that one should be multiplied by this numerator, that extra factor numerator. Is it clear? So I'm going to put them together and write one single expression. I'm sorry that there is even no room on the blackboard to write all these equations, so we have to patch them together like this. It will not fit here. Okay, so let me write the common factor. I'll try to fit it here. The common factors are, after that explanation, 2 minus n over 2. This is that object times what we have from here. That and the denominator to the power minus n over 2. That's the same in both of them. And big bracket, I'm not writing the pre-factors yet. No? There is a factor of I over 4 pi to the power n over 2, which is coming to both of them, but there's a minus sign here. That minus sign is important. That minus sign is on the first factor, which has minus, and there's an eta mu nu, which survives from there. Therefore, the first expression will be minus eta mu nu, m squared minus k squared x, 1 minus x, x times 1 minus x. That's it. So this comes from that. And eta mu nu comes from that numerator. And then the rest of these things we should add to it. And those are plus x times x minus 1 times 2 k nu minus eta mu nu plus m squared eta mu nu. In fact, the only thing which I have not written here, if I write that extra factor also, then I have written essentially everything. Is first of all factors of I over 4 pi to the power n over 2. Which is common to both of them. We took care of this minus sign here. And then there is a 4 which came from tracing over common matrices. So we should multiply this by 4 and put the denominator here. what's left? I think what's left is just integration over x. In fact, this is everything that we needed to write, and this expression is just I pi. So I patch it together bits by bits, but eventually this is what you get.
In the braces, can't you cancel the first and the last term?
So you have to wait a little bit. You can do a lot of cancellation, but this is not in the form that we want it to be. We want it to be in the form that I wrote there, this transverse tensor times the function, scalar function of k squared. This is not in that form yet. Structurally, you see there is a 2k mu. I mean, it's different. But if you work it out, as you have noticed, then it will come to that form. Because there is this term and that term there, and then there is this minus k squared x times 1 minus x.
Should be a case.
There's a k squared here, I'm sorry. Right. So this term times that plus this should be the 2 that we need in order to factor out the 2. And we have to pay attention to the signs. This is that times that becomes plus x times 1 minus x, but here we have x times x plus x minus 1. So in order to bring it to that form, I'll change the sign here to the minus and write this 1 minus x. Okay. Then both of them come with plus. And this minus times this comes with minus. And therefore the structure will be exactly like that. And m squared terms, of course, cancel. So the remaining terms, if you just add them up, and the signs are correct as they stand here, you see this minus times minus is plus. This factor now is common to both of them, x times 1 minus x. So the product of 2 minus gives you a plus. It's k squared times the factor, and the coefficient of k squared is again plus here. The coefficient of k mu k nu is minus times the same x times the factor. Therefore, it is minus k mu k nu plus eta mu k squared. So it is the opposite side, it's the same factor as there. So now I can erase all these things and write the clean expression. Any questions? The reason why we did this, the calculation was actually to see that this works out precisely to the form that we wanted to become. That was the reason for this rather lengthy calculation. Okay, so the final expression is actually I is also cancelled. Now this I, can one of you tell me where this I came from? Sorry? It came from weak rotation. In order to do these integrals, you have to do weak rotation, and you remember it replaces the k0 by I times k4 over kn. And this I was formed with the definition of pi. So the two i's cancel, and the final expression then becomes pi of k mu equals to 1 over 4 pi power n over 2, 0 to 1 dx. There is a factor, common factor of 4. We put it here. X times. Again, I've changed the sign here. I mean, here I have x times 1 minus x. For some reason, I have written it x times, in fact, 2 x times x minus 1. That's a very good thing to do. Instead of changing the sign of that term, I'm changing the notes to sign of that term. Because I don't like minus signs, otherwise there will be minus sign or minus sign in front. Times k nu minus k squared times eta mu nu. I have factored m. In the denominator there's an m squared. If you factor out, it will come out as m to the power 4 minus n. Then times gamma of 2 minus n over 2 divided by 1 minus x, 1 minus x, k to the power 2 divided by m squared divided by to the power 2 minus n over 2. Okay? One thing which I did not tell you was that in 4 dimensions, pi had the mass dimension of 2. We calculate that there were 6 powers of p in the numerator and 4 powers of p in the denominator. It was a quadratically divergent integral. When you go away from 4 dimensions, it doesn't have the mass dimension of 2 anymore. Because now you have n plus 2 in the numerator and 4 in the denominator. This is one of the reasons that we introduced this arbitrary mass parameter mu to the power that compensates this extra powers to keep it dimension 2 in every number of dimensions. I did not introduce that mu, right? But if you had introduced, that mu would stand here, and together with n would give you a log of m over mu, or mu over m. Okay? That's not important for this calculation. It will come back later on. Huh? Because we are going to go to 4 dimensions, and as n goes to 4, you see that this becomes just 1. Okay? And the argument here is dimensionless. That's the reason I factored out the power of m. But you could have kept that, you could have introduced that mu to the appropriate power, and then you would get a ratio of mu over m to the power 4 minus m. I wanted to calculate this, to keep this calculation just to the bare minimum, because it's lengthy enough as it is, and put the finger on the essential parts of it, which that factor of mu also important, but it's not essential for what we want to do here. Okay, now the rest is what we did before, namely define delta, which is 4 minus n, and study the limit of n going to 4 or delta going to 0. And then use the expansion for gamma functions. Then with this notation, we will get the gamma becomes gamma of delta over 2, which is 2 over delta minus the Euler number plus times over delta. Gamma. In the notes, you will find a little bit more of these details of this expansion, etc. Let me erase. Now I can erase actually everything. So I think since we have gone through this kind of step maybe twice when we were discussing phi cube, the self-energy graph or the correction to the provocator of phi cubed, and then coupling constant renormalization for phi to the 4, we had exactly the same kind of expansions. I think now we can I can be a little bit shorter. I'm not going to go through all the steps. I'm going just to write the result of that substitution and expansion. So there will be minus 1 over 4 pi 2 over delta minus gamma times k mu minus eta mu nu k squared plus 1 over 2 pi power 2 k mu minus eta mu nu k to the power 2 times 0 to 1 dx x times 1 minus x logarithm of 1 minus x 1 minus x k to the power 2 divided by m squared. So as promised, the whole expression is, if you factor out this k nu minus eta mu nu, the rest is just a scalar function of k squared. It's a constant piece coming from here. It's a 1 over 2 pi squared times this logarithm function of k squared. Okay. So this whole thing has the structure of k nu minus k squared times eta mu nu times pi of k squared. Where pi of k squared you can read from the coefficient of k nu minus eta mu nu times k squared. And it has two pieces. One piece is the singular part, the 2 over delta. When delta goes to 0, when we go to 4 dimensions, that will diverge. So that's the effect of the quadratic divergence. And then there is a piece which is completely well defined and finite. Okay? This expression for pi should go back here. It should be inserted here. Then we will obtain W to one loop. W up to the quadratic terms in A. Right? And we have to see now what we're going to do with the singular piece. So I will go step by step. First of all, when you substitute this finite part, non-singular piece, it will just be sandwiched between two A's, and this will give you something. What we would like to do is first to understand what's going to happen here. When we substitute that part, the coefficient of this term is just a constant. It's delta dependent, but it doesn't depend on k squared. It's just this tensor times a constant. It has the same structure as the classical part. The classical part is precisely the same tensor or minus the same tensor. No, it's precisely the same tensor times a constant. So when we plug W pi in here, these constant pieces will just add up and multiply the same tensor. Okay? So substitute pi mu nu from star in WA above. Star is here. So we get the following expression for the W. Now we are back in 4 dimensions. So there is a as a prefactor in W. Then there is this tensor, which is common to both of them. In fact, it's common to everything. So I will put it. I'll put it as a common tensor in order for the whole expression to fit on the blackboard. So minus k squared eta mu plus k mu. This is the same expression that I wrote I wrote this factor first and that factor second. Then in the coefficient of this term, there will be 1 over E0 squared coming from there. Then there will be this quantity from here. That's the constant piece. And then the remaining part is the same tensor times an integral from 0 to 1. I think here there was a misprint that's showing minus 1 dx x times 1 minus x times logarithm of 1 minus x times 1 minus x times k squared divided by m squared. So this is, that's our expression. So there is a constant piece here, and there is the effect of the of the loop. This is our effective action for the Maxwell field when you take into account the effects of the one loop coming from the Fermion integration.
So you should have an additional A tilde at the end.
That's right. As usual, I dropped something. That's right, thank you. I have an additional A tilde. Where should I put it? Maybe I can just stick it here. A tilde, new K. Have I written everything?
In the expression where you, the final expression that you wrote for pi nu, in the first term, you should you have minus 1 over 4 pi squared?
Yep. I guess so, yes. Yeah, it comes from that's 2 pi over. Yes, thank you. In fact, here I've written minus 1.
You've written.
Okay, so what are we going to do with the simulator? You should be able to guess it because we have seen similar things before when we were discussing the scalar field, when we were doing the coupling constant or wave function renormalization. The point is that we know that this tensor sandwiched between two A's will give you, in the X space, it will give you just F mu Newton. So the constant piece, constant part, will give us when you go to the X space, it will give you this times simply what you have there. After all, we get that term from expanding precisely this term in Fourier series. It will give you that. Okay? In fact, with the minus 1/4 pi. Now, this object, you can abbreviate it if you like and call it 1/e squared. But it's more than simply an abbreviation. Because experimentally, all you can measure is this combination. You cannot measure separately 1/e0 squared and then this other part. So this is the renormalization of the coupling constant. Although it came from the studying of the one loop effect on the propagator, but we were calculating like one loop correction to the photon propagator. That's the graph that what we were calculating was this graph, no? And that corrects the photon propagator. But nevertheless, E, which plays the role of the coupling constant, becomes renormalized by studying the one loop graph of the photon propagator. This is the hallmark of the gauge invariance, that the coupling constant and wave function renormalization are related. There will be more talk about this later on. For the time being, you can just say, take this simply as the renormalization of the pair coupling, in the sense that you take the pair coupling and add to it the divergent piece and call it a renormalized coupling. So what stands in front of the new term now will be the measurable electric charge, or the coupling constant. Okay? This is precisely the philosophy which we adopted when we were discussing the renormalization of the scalar theory. Redefine the pair couplings in terms of something which we call the renormalized parameters. Okay? And since this is an important topic to which we will return more than once, let me just invert these relations and write it in a form, and maybe introduce even a symbol for later reference. So you can just rewrite that expression in the following form, and you see that this has the form of E0 equals to renormalized coupling times the renormalization constant. You remember for the scalar field we had a similar thing. We had the pair coupling equals to Z1 times lambda. So here I'm calling the analog of this Z1, I'm calling ZE. Where ZE you can read from the expression here. This is E squared, okay? To read the ZE, you have to take the square root of this and keep in mind that this calculation is a one loop calculation. So you should not keep in taking the square of this expression terms like e to the 4. Therefore, to the order that we are studying, Z will be, I guess I messed up with this sign, that should be plus. It is no. Okay, let me write the expression, the final expression the way I want to write it. This 8 comes from taking this to the power 1/2, so that will give you 1/8, and 2 for delta minus gamma. This is it, E, and we will come back to these notations later. For the moment, what I would like to do is to conclude this lecture by writing the expression that we have here in the final form. So just let's take this expression replace this constant part by 1 over e squared. And now, in fact, what I want to do is to send A to E times A. Then E disappears from the first term and D appears in front of the other term. I'm doing this for the next lecture, actually. And write the expression in the form let me go back to the momentum space and copy from my notes. This is the form that we will need later on, therefore there is no need to rewrite in an alternative form. That times a big bracket. Now that we have gotten rid of this whole thing, it's replaced by 1 minus e squared divided by 2 pi squared integral from 0 1 dx 1 minus x times logarithm of 1 minus x times 1 minus x times k squared over m squared. And bracket closed, this closed, and this time I will not forget to put the factor of a at the end. Very long expression. Again, for next time, I'm going to give a name this whole loop correction and call it pi k squared.
In the last expression, the first factor of a tilde should have minus k.
Yeah, this also should have minus k. Thank you. So, just to write, to put it in a form which fits on the blackboard, let me copy the last form here and come back to its users next time. So we have the 1 from the classical part plus pi of k to the power 2 times a tilde mu k from the quantum part, where pi is this whole expression. Okay. Have I written everything? So this is the bottom line. The cleaned up one loop renormalized effective action for the background Maxwell field has this simple form. And all the physics of one loop correction is hidden in this factor pi of k squared. So we have to examine this integral in order to discover what physics is contained in it. Okay?
The mass which appears in this calculation, is it the bare mass or renormalized mass?
Good question. At this stage, it doesn't make any difference because the renormalized mass and the bare mass differ at least by a factor of coupling constant, 1 power, 2 powers of coupling constant, right? So if you replace this by renormalized mass, it will change the change, the correction will be of higher order than we consider. But in the fully renormalized theory, if you write everything in terms of the renormalized fields, renormalized coupling, renormalized mass, automatically what you will get there will be renormalized mass, plus the relevant quantity terms. Okay? Mind you, here I did not renormalize the wave function. I did not renormalize A, I renormalized the coupling. But you see that since the coupling enters in front of everything, in fact, at least intuitively, you should see that instead of, I could do the things differently, in the sense that I could absorb the infinity by renormalizing the wave function, which you can do only in gauge theories. But again, we will discuss this in more detail later on. Which means essentially that the number of the renormalization constants in the gauge theory is less than what you introduce blindly into the Lagrangian. Gauge invariance establishes a relationship between them. Okay, so let me stop here. Any questions? I don't know if this calculation was, you were able to follow what I was doing. I mean, more than this, would we just do step by step all the calculation of the trace, etc., which would take 2 lectures. I encourage you to go through the details of this calculation every step. If you haven't done before, please do that. Otherwise, you will never be confident about QED. It's just playing with tensors and taking traces and things like this. There is the only new thing that we did here, which we have not done before, was in the last step of the renormalization. The few words which I said in the last step. The rest is just a sort of more complicated version of the calculation which we have done before. Complication comes from the fact that you have 4x4 matrices, the Gamma matrices. A tensorial structure, which is an algebraic complication. It's a trivial complication in principle. Okay? There is no conceptual complication. Conceptual complication is related to the gauge invariance. You have a question?
But about the homework. You asked us to derive in the rolling loop. You have a loop and a Fourier loop with external isophotons. You asked us to derive it also with rules, right? So we can assume the final rules already in a
Sorry, so what was the exercise? I asked you to derive it also? Using final rules? Yeah. Okay.
Can we assume already the final rules in position space, or we have to use the final rules in momentum?
You can do it in positions.
Or I can use directly Quiz theorem to make it even more straightforward.
No, the only thing, I mean, you can do it, of course, for actual calculation, it's more convenient to use Feynman rules in the momentum space. Huh? But the major part of this thing is not to do the integration over K, the loop integral. The major part of the question is just commissive set of the combinatorics. If you are convinced of the combinatorics, then you have proven it. To show that the combinatorics of the Feynman graphs work correctly with the n external lines. Okay. I mean, apply the Feynman rules. This is a one loop graph.
Yes, but
and then n external photon lines. Yeah. So you have to apply the Feynman rules to write out.
In position space, is okay?
Yeah.
Okay. That's fine.
Okay. Just the combinatorics. If you want more interesting problem of the same kind, is you can use the formalism that we have developed to calculate the determinant of the Dirac operator as well as in the background of the field, as well as the determinant of the Klein-Gordon operator in the background of the field, like for example a scalar field. I think I gave you an example of 2 scalar fields that coupled to each other. You can use the Green's function equation both for fermions and the scalars in the background of a field to calculate the determinant of Klein-Gordon operator or the determinant of Dirac operator. Okay? If you work out that, starting from the Green's functions. No path integrals, no functional integrals, just Green's function. That means canonical quantization, right equation for the Green's function in the background of the field. Use that to obtain the determinant of the Klein-Gordon operator in the background of that field, or the determinant of the Dirac operator in the background of that field. You will discover that the determinant of the Klein-Gordon operator comes with the power of -1/2. The determinant of the Dirac operator comes with the power of +1 or whatever. You can take actually a complex scalar field in order to have the powers to match. For example, if you take a 2-component complex scalar field, it will have 4 real components, and therefore the power of the determinant will be -1/2 to the power 4. Okay? Then it will match, it will be like the Dirac operator. Or take 2-component to match like the Dirac operator. Did you understand the exercise? No.
I'm a bit confused right now.
No. Okay, let's just take the Klein-Gordon.
Okay.
Take a scalar field. Couple it to another scalar field called chi. Write the Green's function.
What type of coupling? What type of coupling?
The coupling that I gave you in the exercise, chi times phi squared.
Ah, okay. You're talking for the next exercise.
Chi times phi squared. Write the equation for the exact Green function in the background of this chi field. You can use that to calculate the determinant of the Klein-Gordon operator, the Green function equation. Calculate the determinant of Klein-Gordon operator, you will see that you will get the determinant to the power -1/2. Repeat the same exercise for fermion coupled to a real scalar, it doesn't matter. Again, you will get the determinant of the Dirac operator to the power +1. And that will prove that what we did, the rules that we invented for the fermionic integration were correct.
You are saying that
without using fermionic integration. You will derive it without using fermionic.
Yeah, so you are saying that without using path integrals.
Without using path integrals, you can obtain the determinants in one case with positive, in another case with negative power.
But in the context of path integrals, we do know how to define the determinant. So how do we define the determinant in the canonical
No,
form?
determination, the initial determinant doesn't depend on the path integral. You obtain a determinant, now calculation of that determinant has nothing to do with the path integral. You have to calculate it. The path integral led to the determinant. Now, the way you're going to calculate the determinant has nothing to do with the path integral anymore. Is the exercise clear now? Okay. That's an optional exercise. Whoever wants to learn this subject deeply, try to solve that exercise. Probably most of you probably didn't even pay attention to see what the exercise was. So, you don't solve it. Good. If you want, I can formulate, I can write precisely what the exercise is. You want it?
Yes.
Let's just do it. It's not hard. Let's not postpone it. You have to solve all parts of this exercise by yourself. I'm giving you the problem, not the solution and not the guidance. The guidance I'm giving you, but the solution no. So take L as 1/2 phi minus e squared minus m squared plus chi times phi. Okay?
Phi is the complex.
Chi is a real field. So phi and chi, real. Phi and chi, real. The aim is not the power of the determinant, what the number is, but the positive, the sign of the power of the determinant. This is the aim of the calculation. You remember that for boson it came with minus power, and for fermion it came with plus power. Obtain the equation for the 2-point function. use this equation to obtain that minus no passing thing. That's canonical quantization. Okay? Repeat the same exercise. For L equals to psi bar IT slash minus M plus chi times psi. Again, chi is a real field, doesn't matter. Repeat it, the same thing. Obtain Fermionic 2-point function. Obtain means write the equation for Fermionic 2-point function, and from there derive the result of that power IT slash minus M plus chi to the positive power. So without any use of the fast integral, you will see that using canonical formulation, that will give you the Fermion determinant plus positive power, and that will give you the bosonic determinant with minus power. That justifies then the rules that we invented for obtaining the Fermion determinant.